Hello, class. This is Mr. Hart, and in this podcast, I want to go over the solutions and pH chapter in our textbook. Okay, so we don't cover this a lot in eighth grade because it's not on the core and it's more of a chemistry topic, but I like to give you a little bit of background on solutions and pH because I think they're important. They're very commonplace ideas. We'll get into acids and bases, and there's things that are common in like household chemicals and cleaning supplies. So I think it's important to know what these things are and how we measure the strength of these things. But again, we don't get to cover this a lot because it's not on the core. But I want to give you guys a little bit of background on these topics. Okay, so um, let's just start with what a solution is. And so hopefully you remember from a few units back that a solution is a mixture where a substance completely dissolves, like, salt water or sugar water, or like a drink mix like Kool-Aid or something like that. Okay, so a solution is, a homogeneous mixture in which particles are too small to reflect light. Basically, they completely dissolve, is another way of saying it. So hopefully this is an idea you remember from a couple units ago. Okay, but just keep in mind a solution is some type of mixture. Okay, and we also have two other vocabulary words we want to introduce, which is soluble and insoluble. Okay, so something that is soluble is able to dissolve into a solution, and something that is insoluble is unable to dissolve. Okay, so for example, sugar is water soluble, meaning it can dissolve in water. Okay, whereas baking soda, for example, is not water soluble. You cannot dissolve baking soda in water. Okay, um, so keep that in mind. Soluble meaning able to dissolve, and insoluble unable to dissolve. Okay, so this is kind of some background on solutions and things we want to keep in mind. Some vocabulary we want to know when we're talking about mixtures. Okay, and so the next thing we covered is what actually happens when you dissolve something like salt. Okay, so the reason water is such a good dissolver of things, you could say, is because it's a polar molecule. So when something like salt is put in it that has the positive and negative ions, okay, the water will actually kind of surround the negative ions, right? Because if you remember, water is polar, so it kind of has a positive side near the hydrogens and the negative side near the oxygen, okay? So those hydrogens naturally kind of group around the negative ion and they kind of push away the positive ion, okay? So as the water is able to get all this stuff, as the water is able to kind of surround all these negative ions, okay, it is able to dissolve the entire material throughout the substance, okay? And even something like sugar, for example, which is not, an ion or ionic compound, it's not charged. Water can still dissolve this because it can take these crystal structures like there are in sugar, and again, kind of surround them still and break it apart. So no matter what it is, water is very good at dissolving, okay? As long as there's enough water, it usually can dissolve most substances. Okay, and we saw a demonstration here that water is able to kind of dissolve as much as it can until it reaches a limit. Okay, if you put too much salt, it no longer has enough water molecules to break everything apart. Okay, but as long as there's enough water, it's able to dissolve many substances. Okay, all right. So, in some other vocabulary terms we want to know, a solute and a solvent. So, a solute is a substance that gets dissolved. For example, like a sugar cube in water, the sugar cube would be the solute, and the solvent is the substance that does the dissolving. Okay, like water. Okay, it's the thing that's dissolving the thing. It's dissolving the solute. It's dissolving that apart into the substance. Okay, so you put sugar cube in water. The sugar cube is a solute. The water is a solvent. You have a drink mix like Kool-Aid or lemonade powder or something like that. The lemonade powder is the solute. The water is the solvent. Okay, you're dissolving salt in oil, which doesn't really work very well. But in that case, the salt would be the solute, and the oil will be the solvent. Okay, so just keep that in mind. And again, a lot of vocabulary terms, but it's just kind of good to know because we use these words a lot in kind of everyday vocabulary. So we want to make sure we understand what these things mean. Okay, but let's look at some of the properties of solutions. Okay. One interesting property of a solution is that it has a lower freezing point than normal. Okay. It has higher boiling points than normal generally. It usually is better conductors than normal. So, for example, if you have salt in water, okay, that salt makes the water have a lower freezing point, which means if you put it in the fridge or in the freezer, it would take longer to freeze or wouldn't be as icy or frozen as normal. It makes it harder to boil. So if you put salt water on the stove with regular water, the salt water is going to take longer to boil as well. Okay, which is actually a good cooking tip, by the way. And then the last thing is it makes it a better conductor. So if you have a light bulb circuit wired through salt water and one that's wired through regular water, the light bulb that is through the salt water will actually shine brighter. Okay, because the salt makes it a better conductor. So this isn't always the case, but for most solutions, we can expect these three things to occur. Okay. So here's a practical application of this antifreeze. Okay, so if you ever put antifreeze in your car, know what that is. It's something you put in your carburetor so that the certain fluids and gases in your car won't freeze as quickly. Okay, meaning if it's a very cold winter day, your car can still start rather than all the fluids being frozen over because it was too cold outside. So the antifreeze is a solution that helps bring down the freezing point of all the fluids in your car so they won't freeze over as quickly. Okay, so that's a really good practical application of this. Okay. All right, so you're probably wondering why are we talking about all these solutions and all this stuff when we kind of already covered it a little while back. And the reason is because it doesn't make much sense to talk about acids and bases until we've talked about solutions. Okay, so the main thing we're trying to get to is acids and bases. So you've probably heard of an acid before. You've probably heard of battery acid, and you may know that like lemon juice is an acid. Some of your household cleaners are acids. You may have seen in movies that, there's pits of acid and all these like dangerous scenes with acid. And so it kind of has this negative context, but really an acid is just a solution, okay? And it's a solution with a kind of an ionic property, okay? And so we'll get to that in a second, but just keep in mind most acids, or pretty much every acid, is just some type of solution, okay? Just some type of solution that has some specific properties, okay? And then there's also bases. Most people don't know these as well, okay? But if you've ever seen like baking soda, that's a base, or a base, sorry. If you've ever seen baking soda, that's a base. If you've ever seen like drain cleaner, that's a base. Concrete and certain types of limestone and detergents are bases, okay? So these things are also solutions, believe it or not, okay? They also have ionic properties, and we can kind of classify them. They're usually kind of, think of like a bitter / tart feel to them, taste to them, okay? Think of baking soda, think of ammonia, those types of things we associate with bases. And so here's the key idea of the separation between an acid and a base, okay? So they're both ionic solutions, okay? But an acid is an ionic solution that contains the H plus ion, and the base is the ionic solution that contains the OH minus ion, okay? So you probably heard of acids, maybe you heard of bases. They're both solutions. They're both ionic, which means they kind of have this charge property to them. But the acids have the H plus ion and the bases have the OH minus ion. Okay? So if you think about it, if I take an H plus, let me change colors really quick. So if I take the H plus ion, okay, a hydrogen with a positive charge, and I take an OH ion, oxygen and hydrogen combined, with a minus charge, and I combine those together, you can imagine what I'm going to get is H2O. or water. Okay. So the positive and minus cancel out. We combine those together, we get H2O. Okay. So I like to think of acids and bases kind of being the opposite of each other. Okay. Acids are trying to find that OH ion to become water. And so they're kind of going to eat through certain chemicals and things like that in order to find that OH minus ion. It's going to pull that out of certain chemicals and things like that, which is why acids are known to be so corrosive, so dangerous. They kind of eat through stuff because they're trying to pull out that OH minus ion. They want to be like water. Bases do the same thing, but in the opposite direction. So they don't want OH minus, they want this H plus because they want to become like water. So they also will eat through certain chemicals and pull out those molecules until they can become like water. Okay. So acids and bases are very reactive generally because they want to get to this more stable state of water. Okay. And so they're going to kind of eat through things as they try and get to this state, which is why they're such good cleaners usually. They're such good, corrosive solutions. Okay, they eat through lots of things because they're trying to find that those molecules to become like water. Okay, so hopefully that makes sense and it gives us kind of an idea of what acids and bases do and why they're so reactive. Okay, and so the last thing we want to talk about is what we call pH. Okay, which is basically parts hydrogenide, or basically the H plus ion. Okay. So parts of the H plus ion. Okay. And so pH is a measure of the strength of an acid or a base. Okay. So imagine you're like a forest ranger and there was a little bit of acid rain the other day and you're trying to test the amount of acid in the water. Okay. Because you want to make sure that the animals and the fish and the wildlife aren't in harm or in danger from that acid. Well, in order to do that, you need to have some type of scale of how much acid or base you had. Okay, so that's why they invented the pH scale. It's a way of telling how dangerous an acid or a base is. If it's something that's really light, not that strong, then we probably don't have to worry about it. If it's something that's a very strong acid, then that's something that concerns. In order to do that, we need some consistent way of determining how strong these things are. Okay, so that's why they invented the pH scale. This is kind of how it looks. Okay, it goes from 0 to 14. Okay, it's kind of an interesting scale. It goes around 0 to 14, and 7 is actually the middle line. Okay, so everything above 7 is a base. Okay, again, apologies for the poor spelling on the touchpad. But everything above 7 is a base, and everything below 7 is an acid. Okay? And so the further and further you go down the scale, from 7 down to 1, that's the stronger acid. So gastric acid is probably one of the strongest acids we know of. Okay? But if you go higher and higher and up the scale, that's a stronger and stronger base. Okay? So bleach is a very strong base. Another one is like liquid Drano, drain cleaner. I know that's a really strong base. It eats through a lot of stuff. Okay. But hopefully you kind of see the point here, or kind of see the distinction. So if an acid is down here at 1, then we know it's a very strong acid. We probably should stay away from it. Or if it's up here at 14, we know it's a very strong base. Probably should stay away from it. But if it's only an 8 or 6, we know that's not a very strong acid or base, and so we probably don't have much reason to be concerned about it. Okay, like milk. You drink milk almost every day. Okay, so I mean it's officially an acid, but it's not a very strong acid, so it's not much concern. Okay, so that's the pH scale. Hopefully that makes sense. And the other thing that's nice about the pH scale is we can determine what things are going to neutralize each other. So let's say we have an acid, a very strong acid, maybe like orange juice, okay, and we want to neutralize it so it's not so acidic, it's not so strong. Well, if we're at 3, and that's 4 below 7, 1, 2, 3, 4, then we want a base that's as strong as this is an acid, okay? It sounded a little confusing, but hopefully kind of see what's happening here. So we're going to go 4 up on the base scale. So we'll go to 11. So if we combined ammonia with orange juice, a very strong acid with this very strong base, then we'll get something that's neither an acid or a base. It's pretty much neutral, like distilled water. Okay. So again, this is also useful because we can see how we can combine things to make things more neutral. Okay. And in class, I did a demonstration where I combined baking soda with vinegar, and I was able to neutralize them so they basically look like water. Okay. So really interesting, really cool. Using the pH scale, we can kind of again neutralize these different acids and bases. Okay. All right, and then the last thing I want to talk about is what we call a pH indicator. Okay. And so what a pH indicator does is usually they're found in little like paper strips. And so let's say I have an unknown solution and I want to know how strong of an acid or a base it is, then I can actually kind of dip these little paper strips in there into that solution. And based on what colors come out, I can tell what type of acid or base it is. So let's say I dip that little strip in there and then the colors on the strip of paper end up like this. Sorry, hopefully you can see that. But if I see these colors on that paper strip, then I know that it's probably a pH of 3, which I know is a pretty decent acid. Okay? And so these indicators are how we can tell what pH a solution is. Okay? So you just dip the indicator in and you can see what the pH is. Okay? And then we watched this video, which I highly recommend, can be found at this web address. But it's Steve Spangler, and he uses a liquid indicator. So he puts different solutions in this liquid indicator, and he's able to determine the pH of them. Okay, so these just help us out to actually measure this effect of how much acid or base we have. Okay, that's what an indicator's purpose is, to tell me how acidic something is or how basic something is. Okay, but that's all we're going to cover for solutions and pH. Hopefully that gives you, again, a little bit of background. I know we didn't get a lot into it, but if you kind of find this interesting, I recommend looking more into it. But that's all we're going to cover for now. Hopefully that made sense. And let me know if you have any questions. Thank you for watching.